Welcome back, and we are almost towards the end of our course on electronic packaging and manufacturing. And what we would do over the next couple of lectures is look at some specialized topics. Okay, as I said, this is such a vast field, and there are newer and newer challenges coming up almost every day, and thousands of engineers across various disciplines are working across different companies, different universities, different research labs all over the world, trying to solve these problems and come up with new technologies, okay, and trying to keep up with the current trends in the electronics industry or even in the whole overall industry, because more and more, our life is getting more and more involved or integrated with electronic products. Right. You think about it, the car that we used to drive maybe 50 years back, it was primarily mechanical, maybe with a few electrical circuits for the lights, the headlights and so on. Today, automotive electronics itself is a field where thousands of people, tens of thousands of people are working. Okay. Avionics on the other hand, of course, aircrafts did have a lot of some electronics traditionally, but now the amount of electronics that goes into the aviation industry, it's just mind blowing. Okay. Printing press, okay, that I think we all know. We have seen printing press, we as in my generation, maybe who were born in the 70s, we have seen printing press, completely mechanical ones. But you know how the printing presses look today, and how much involved we are, how we have got involved, or our printing process itself has had the impregnation of electronics inside it. Okay. So, what we are going to talk about today is one such field where the electronics is becoming so important, and that is energy. Okay. So, we are going to talk about power electronics packaging, and that is the topic of today's lecture. We are going to talk about first what is power electronics to start with, then power electronic devices, what are the packaging challenges, and then a summary. Okay. So, these are just to give you a flavor of some very important fields and some very fields of current relevance where there is a lot of concentrated research today. Okay. So, power electronics, how do I define that? To put very simply, it is electronics that is used for power generation, distribution, that also requires transmission, and conservation. Let us think about it. What is power generation? Okay. What is power generation? If you talk about how do I generate power today from new and renewable sources or non-conventional sources, let us say wind, let us say solar, you would be surprised, and you would be, it's really mind blowing, mind boggling to see how much of electronics is involved today. Because if you look at a photovoltaic panel, it is not just enough to convert the solar energy to electrical energy, which itself is what the photovoltaic cell does, but thereafter how do I store it? How do I transmit it? How do I transmit it intelligently? Right? Is it going to be a standalone solar system, or is it something that is generating power and supplying to the grid? That comes in the distribution part, generation, distribution, conservation, batteries, the battery management system, how much am I going to draw out of that? All this is power electronics. Look at some pictures that I have put over there. The first one is about the field of electric vehicles. We are talking about plug-in electric vehicles, we are talking about hybrid electric vehicles which runs on both electricity as well as fossil fuel or natural gas. So, these are, and if you look at an electric vehicle, the electronics is involved in transmission, in the battery, in running the motor, controlling the motor drive, plus running all auxiliaries, accessories. Okay. All right. If you look at power backup, right, the UPS, we have it for our desktops, the smaller versions, that is electronics. Electric drives, hybrid cars, electric aircrafts, no more aviation transmission fuel. Okay. Battery management systems, if battery is something that we look at for energy storage, then how do I store it intelligently, how do I look at its health and draw the current during discharging phase intelligently, that is controlled by electronics and smart electronics, right. Wind turbines, in wind, if you talk about wind energy, wind turbine, how do you control the storage of the wind energy, okay, the mechanical energy to electrical energy using the generator, okay, very important, and how do you transmit it to the grid. All right. So, power electronics is an area which is extremely important today, and it has its own challenges, because see, so far, even though the concepts that we are discussing in this course are very generic, I think the examples that we were drawing are kind of products that we use every day, smartphones, tablets, laptops, desktops, servers, mostly in the computing world. But here the main difference is, but over there is not much of power energy storage or distribution, conservation, or forget generation. All these have a power source either from the plug point in the wall socket, or in a battery, from a battery. But here in power electronics, it is about generation, conservation and distribution or transmission, right. You see a power electronic module over here, this is a converter. University of Nottingham, one of the universities across the world with which is very strong in power electronics research, both in the electronics part, packaging part, reliability and thermal management part. Okay. They are the hub of a very large consortium in Europe. All right. So, therefore, what is the motivation? If you look at power electronics, it is everywhere. It refers to systems which process and control the flow of electrical energy, converting it from one set of voltages. So, this part we did not talk about, I am going to come to that. Voltage step up, step down, okay? One set of voltages, currents and frequencies to another, which is better suited for user loads. If you look at a power station, the generation is in kilovolts, right. The high tension wires that run over our fields, you touch it, you will be electrocuted in an instant. What comes to our wall sockets? 220 volts in India. That itself is quite high. Of course, you have seen some generation houses, maybe where generators are stored, or these electric distribution panels are stored, you will see danger 440 volts. So, there is a further step down to 220 volts from 440 before it reaches our household, and it is still not safe. You touch it, it is going to be very harmful, even fatal in certain cases. In USA, it is 110 volts. It can lead to electric shocks, but probably the impact is going to be less dangerous or probably not fatal. Okay. That is why they have it at 110 volts. Of course, their currents are higher, right. So, energy efficient. So, therefore, if you look at the power converters and inverters, AC to DC, right, or DC to AC, correct. So, AC to DC you require where? In computers, in radios, in cell phones. When you charge a cell phone, it is a DC output, but what comes out is a socket, right. Often we call it an adapter. If for people who are into music, or at least are fond of music, the synthesizers or the keyboards, the Yamaha, the Korg, Roland, if you look at them, the input that comes in, which is the adapter, is DC, 12 volts DC, right. So, that black box is actually converting the AC 220 volts from your plug point to the required DC volt that is required as input for your synthesizer to play. Okay. All right. AC to AC in AC motors, power systems, it is still AC, but I am stepping it down from kilovolts to 220 volts. DC to AC inverters, where do you need it? Solar energy, photovoltaic, right. You need an inverter, you store it in batteries, then you need an inverter. DC to DC microprocessors, okay, step down transformers for example. So, for example, I stayed few years in US during my postgraduate studies, doctoral studies, and later I also worked for a few years there before coming back to India. And when I moved back, I had several appliances that were bought from US, and either they were good or they had some fond memories associated. For example, when I was a student, I bought a microwave oven, I still have that. I wanted to have that one piece of memory from my student days. So, I still have it. Actually, so when we came back, I wanted to run that. Now, I do not run it anymore, I have another one. It has been 15 years since I came back. But if you think about it, when we first came back and I wanted to run, I wanted to run them, I needed a step down voltage transformer or a converter, because those are designed for 110 volts. If I plug it into our 220 volt supply, they will just, they will conk off, they will go bad. So, these are all power electronic devices, isn't it, right? Okay. So, earlier the step down transformers would be actual transformers with windings, primary, secondary, but now you can step down and step up using ICs, right. So, we will come to some of those. We will talk about BJTs, we will got IGBTs, all that. All right, MOSFETs, field effect transistors. So, energy efficiency, 10 to 15% of the generated energy can be saved by widespread use of power electronics. If you design it properly, why power electronics is important? Because it has this intelligence built in, and you can, the efficiency, the recovery, ultimate recovery, the losses can be minimized, ultimate recovery can be maximized, all right. And environment friendly, because it utilizes non-traditional, it helps rather. Power electronics is essential for your wind turbines, for your solar power generation systems to work, all right. And this is becoming important because now there is so much of focus on new and renewable energies, not so much on fossil fuels. So, as wind and solar becomes more and more important, power electronics is also going to grow in importance. Another example is power electronics in electric vehicles. Okay. So, you see inside an electric vehicle where all we need power electronics, just as an example. There is a battery and there is a battery charger, and that is where the high voltage battery that we are going to use, the battery charger, and also the way how we are going to control the current flow and the current draw and current flow during charging and discharging depends on what is called the battery management system, BMS. 120 volts AC or 110 volts AC, probably in USA and some European countries. For our case, in our country, if this has to become very common, the charging stations has to be 220 volts AC. Okay. And then in high voltage battery, depending on the voltage, you will have a converter, right, DC to DC converter, and then on the other hand to run the accessories, and then you will also need an inverter to run the electric motor, because what comes out of the battery is DC and what you need is AC. So, you have an inverter, then the electric motor which is giving you the transmission, the torque to the wheels. So, everywhere these are power electronics. It is a converter, it is an inverter, it is a switch, it is a battery management system, all are power electronics. This is an example. Okay. So, what are the trends in power electronic packaging? If I look at it, it is increasingly becoming the packaging, and therefore, and that really, and the packaging is so important because that helps in its reliable operation under certain temperature conditions, under certain workloads, under certain environmental conditions. The packaging will determine how effectively and efficiently it works. So, that is increasingly becoming the key product differentiator, okay, in size, in weight, in efficiency and cooling. If you look at a power electronic device from one vendor and from another one, what is going to differentiate the two? These are the ones: size, weight, efficiency and cooling, which is related to that. Here I want to mention, probably it is there in another slide, in one of the later slides as well. When we are talking about computing products, what is rest of CPU power? Maybe 35 watts, 50 watts, server 100 at most, cell phones, tablets 1, 2, 5. When we come here, we are talking about hundreds of watts to kilowatts. That is the power levels we are talking about, that is being generated. Clear? And there 10 to 15% of that is other losses, and finally, that is what we have to dissipate. You can understand how much we have to cool, right. So, if you look at it, used at increased load levels. So, cooling becomes important, the losses become more, cooling becomes more important. In harsh environments, you look at the two examples, one is downhole, you are drilling, right, it is coming down several miles into the ground, very harsh environment, hot harsh environments. Or deep sea, offshore exploration, what do we see there, right? These are also high pressure, may not be so high temperature, but very high pressure. Over here and in the downhole there is a lot of dust, lot of particulate matter, okay, and there is electronics at the tip of this probe or at the tip of this drill, exploration drill that goes down. Okay. I have seen drilling of bore wells in Bangalore at my home, where I used to stay before this. They had cameras. Time and again we wanted to see that what is the level of water in that groundwater level over there. You would go down this pipe and there will be a camera and you could see where the water is coming from. At some point when you go down, you will see one crevice through which the water is coming. It was fascinating. But imagine this is a wire that goes down several kilometers. Actually, if you are talking about some of the hilly areas in Bangalore, you are actually drilling close to a kilometer to get water, and that signal has to be transmitted. So, the electronics, the signal transmission, the minimization of losses, very, very important. You have all kinds of sensors when you drill it, temperature, concentration, pressure, and you name it, right. And denser packaging schemes. So, these are very, very small and you need to have a lot of electronics in them. Okay. So, there is a drive towards fully integrated power electronics module. We will see what a power electronics module is, but what essentially it means is you have a main system and then you have a lot of subsystems and you want to bring them as close to each other as possible. So, again drive towards making more compact electronics at increased power levels, very, very challenging, minimization of losses and effective cooling. Newer materials, the switches, silicon carbide, gallium nitride, these are new materials that are being used, better losses, switching or lesser switching losses, new materials, different temperature limits, thermal becomes important, different materials, the mechanical reliability becomes important, and understanding those, it is no longer lead tin solder, right. All right. So, physics of failure concepts for reliable designs become very, very important. So, what we will do next is we will use the remainder of this lecture to just look at some of the current challenges and then looking at some of these, what are the important power electronic products that are being designed and packaged today. So, this is just a snapshot again from Professor Abhijit Dasgupta's Gyan course. I am sorry, I forgot to mention, I will do that. I forgot to mention on the slide, but I will do that, but I am verbally acknowledging his help here, contribution here. So, you see, if you look at these, the three pillars of research today: high temperature electronics, high power electronics, and thermal management, right. The cooling, reduction of losses, the losses go up as temperatures go up. If you keep the temperature within limits, the losses will also come down, and then the losses are the heat generation that must be dissipated. So, all of these are kind of interrelated, right. If you have losses, you do not cool it effectively, then the temperature goes up. As the temperature goes up, the losses go up even further, the kind of thermal runaway, and as a result temperature goes up even further. So, thermal runaway conditions, clear. What I am trying to say is, in other words, the same power electronic module, if under with a certain thermal solution, it can run at 100 degree C, then the losses is something L1, let us say, some L1 percentage, and I have another cooling solution which can cool it better, and instead of 100 it is at 80 degree C, then you will see that the loss L2 in the second case is actually in percentage is going to be less than L1. Okay. All right. So, you see some of these terms over here. We are not going to go through each of them. TEC, TIM, if you look at the thermal management, which is, you will always see this bias when I talk about thermal, TEC, thermoelectric coolers. We have talked about TIM, thermal interface materials, PCM, phase change material, which is one of the thermal interface materials. Okay. So, these are enablers for high temperature electronics. For high power electronics, where I need to dissipate more power, I really need very what should I say, very innovative cooling solutions. Embedded cooling, 3D cooling, I am going to talk about a little bit about these. Embedded cooling is actually inside the silicon itself, or inside gallium nitride, or inside the device itself you have the cooling passages. It is no longer the chip and then a cooling solution on top, embedded inside. 3D cooling is when you have multiple layers. Let us say you have flow of a liquid through channels, you have multiple layers of those inside the same device. Okay. Spot cooling, you need some area, there is one field effect transistor which is probably giving, or an IGBT bipolar transistor, insulated gate bipolar transistor, which is generating a lot of heat in a very concentrated area. I need spot cooling of that. What can I do? Right. These are different challenges. All right. So, high power electronics involves switches, high power capacitors, and we need to understand what is very important here, system level reliability. Actually, all of these, both in high temperature, high power. Okay. So, let us look at some of these power electronic components or devices. Power converters or inverters. Converter is actually changing the voltage from one value to another, but it is typically AC to AC or DC to DC. Inverter, on the other hand, we know is DC to AC. Okay. Now, these are used in a wide range of applications. We saw some of those. I mean, both converters and inverters we saw in electric vehicles, because the battery is the source of energy, but then to run the motor you need to convert, you need to rather invert DC to AC, and to run some of these low power auxiliaries inside the car, some of the sensors, whether it is your parking brake system or whether it is your music system, the lights, the indicators, the odometer, the speedometer, all these you need lower voltages. So, you need step down converters. Okay. So, power converter actually combines a number of known power electronic packaging technologies that can switching devices, control circuitry, sensors, and large passive components. And when we say passive components, these are like the capacitors, the resistors, these are passive components. Okay. So, power converter is going to have these components inside, power converter module is going to have these components. All right. Power electronic modules, okay, sometimes these are used very interchangeably, but power converter, many people use it, I myself used module in the last slide, but actually strictly speaking, if you talk about a module, it is a multi-chip module, power electronic module, MCM, we talked about this before, right. It consists of multiple power devices, transistors, diodes, etc., operating in parallel to create a switch. Okay. So, I think the electrical engineers, people with electrical engineering backgrounds who probably know much more than me, they will be able to appreciate this further better, right. So, these have the highest power densities, so most difficult to cool as well as losses. Okay. The efficiency is about 95 to 98%. Alright. So, what I am trying to say is highest power sensitivity and probably this should be minimal losses, okay, 95 to 98% efficiency. So, the power dissipation levels can be from 500 to 5 kilowatts, 500 watts to 5 kilowatts. Compare that to some of the computing devices we are talking about, single digit watts, at most 100 watts. Okay. And they can be designed for high temperature operation than the rest of the power electronic systems. Okay. And these are some of the applications, locomotive traction, okay. Electric locomotives, another one, transportation technologies, electric locomotives is very important. Avionics, hybrid vehicle power control, motor drives, wind or solar inverters. Okay. So, over here we see some of these power electronic modules. Okay. IGBT, insulated gate bipolar transistor, that is what it stands for. Okay. So, it is used as switches and inverters in high power circuits. So, if you look at this plot at the bottom, okay, what you can see is the following. If you look at this current rating and this is the voltage rating. So, depending on where we are, depending on the application that we are talking about, you see that power ICs, low power and voltage till a kilovolt, you can use these. But however, as you go up, you need either in voltage or current, you need these other types of transistors. MOSFET stands for, I think everybody with an electrical background will know and probably most other engineers will also know. MOSFET is metal oxide semiconductor field effect transistor, IGBT insulated gate bipolar transistor. By the way, when not us so much, but maybe people who were like 5 to 7 years senior to us, when they were studying electronics, at that time it was BJT, bipolar junction transistors. Today it is almost not used, so very used very rarely, it is primarily IGBTs or MOSFETs. Okay. But BJTs had the characteristic of high current carrying capability, and MOSFET on the other hand was very fast switching speeds, right. IGBT kind of combines the best of both worlds. All right. So, it is becoming very, very important, especially in wind energy generation, high speed rails, hybrid vehicles, very high current carrying capability, you know, the feature that was associated with BJT along with high speeds and high voltage ratings. So, as you can see here, high current, high voltage, this is where IGBTs fall. If you need to go further, then you have to go for thyristors. Power MOSFETs typically are higher current, but not so much of higher voltage. Okay. So, not so high power. All right. Okay. So, power electronics is a different ball game, and so therefore, it has its own unique challenges for packaging. So, I am giving just an example. This is a packaging innovation example for interconnects. So, you go from traditional wire bond to something called sintered interconnect, because here we are talking about, we have already studied wire bonding schemes. Sintered interconnect, what happens is, you can see these are more permanent type of attach, the chip is bonded both in top and bottom with a permanent attach, and you see these interconnections coming out, these are not thin wires. Okay. So, it eliminates the wire bond failures, and it also supports double sided cooling, because you have these metallic surfaces both at the top and the bottom. Okay. If you want to know more, you can read this WBG inverter packaging. I have listed the source over here. If you can get hold of this paper, you can know more about this. The other thing is about increased cooling challenges, because dissipations is of the order of several hundred watts per centimeter squared. It is no longer 30 watts per centimeter squared or 50 watts per centimeter squared, with which itself we were struggling. So, many a times, you know, air cooling in that small area is no longer enough. You have to resort to either very, very large heat sinks, or you have to go for remote cooling, where you use water or liquid to cool for the first level of cooling at that site, and then cool that water using a radiator somewhere else. Okay? Because controlling the temperature is critical to its performance and reliability. We know that. I do not think we need to talk about any further. Performance, if you do not control the performance, if you do not control the temperature, it will be slower switching, higher leakage current, higher losses, and reliability, of course, temperature induced failures. We have all seen how important that is. So, potential thermal management strategies, these are some of the things that are being researched currently. Microchannel cooling. So, microchannel, remember, these are very small channels embedded inside, typically embedded inside the device itself, whether it is silicon, whether it is gallium nitride, silicon carbide. So, remember, we were talking about Nusselt number, and Nusselt number for laminar flow, if you go back, you will see it is a constant for flow through a channel, for laminar flow through internal laminar flow through a channel. And Nusselt number is Hd, which is the hydraulic diameter, H times hydraulic diameter over the conductivity of the fluid. So, now if you go to microchannels, which is very small channels, what happens? The hydraulic diameter goes down, but Nusselt number is constant, therefore, heat transfer coefficient has to go up, because Hd by K is constant. So, for microchannels, you get very high heat transfer coefficients and heat transfer rates, but as I said, nothing comes for free. You reduce the size of the channels, you get more heat transfer per unit area, you get more heat transfer coefficient, but you get very high pressure drop as well, right. We have seen that large fin spacing to smaller fin spacing is forced convection. We are talking about heat sink and fan. The operating point was shifting to the left because the system pressure drop was steeper or higher. So, for a given pumping power, if we are talking about microchannel with a liquid, for a given pumping power, we are going to get less flow through microchannels compared to larger channels. Okay? All right, but microchannel cooling, especially embedded microchannel cooling, is one. Two-phase cold plate. It is no longer water coming in, water go out, but I need to use the high heat transfer coefficients for two-phase flow when it is boiling. Spot cooling, I was saying in the last slide, right, or two slides before. You may have an area where there is an increased power density. I need to cool that, targeted cooling of that spot. And 3D integrated cooling, multiple layers of maybe channels, cooling channels inside the same die stack. If you are going for 3D, it is also true for 3D packaging. When we talked about 3D packaging before, you can have multiple cooling channels through each of them, because you may not have a lot of real estate, you may have to go up vertically. So, you go, so 3D integrated cooling, for example, you go one way, you turn around and come back the other way through two layers of channels. Okay? So, these are some of the examples of current trends in research on thermal management. Okay? So, summarizing it, power electronics is becoming very, very important as a critical enabling technology, and sitting at the intersection of renewable power generation, renewable power distribution and transmission, and efficient power utilization and storage. Everything depends on power electronics, and with the current thrust on energy, especially renewable energy sources, power electronics is only going to go more and more important. The growth of, or the importance of power electronics is only going to grow with time. Okay? The next generation power electronics will use new packaging technologies. We already saw sintered interconnects as an example, 3D integrated thermal management. We talked about briefly DBA substrates. So, these are different types of substrates, okay? No longer FR4, but some new ones, newer materials, newer characteristics, newer properties. And finally, last but not the least, what we were discussing till the previous lecture, reliability. See, these are all new technologies we are coming up with, but do they perform reliably over time? Reliability issues inherent in compact and high power density packaging, including thermal. It is an important research area. Okay. So, that was just to give you a brief half an hour summary of something which is probably one of the hottest topics in electronics industry today, which is power electronics. Okay. It is growing at a rapid rate, both in size and its importance. Okay. So, this is an area also that many of, if you want to get into research in this field of electronic packaging, power electronics probably today, that is the area to get into. We have several groups over here at IIT Kharagpur who are working on not so much on packaging, but power electronic devices, circuits, and it is important that as these electrical engineers innovate, to come up with newer devices, newer modules, the packaging engineers, which involve experts from different fields, come together and work together to develop commensurate packaging technologies that can enable these newer designs, these newer product designs, as well as enable its performance, its reliable performance over its entire lifetime. Okay? All right. So, thank you very much, and when we come back in the next lecture, we will look at some other, maybe a couple other important topics of current relevance. Okay? Thank you very much.